excited to be able to introduce Casey to present her final presentation for her culminating experience. Casey's done a lot of work and really has jumped through a lot of hoops to get this working. She has stayed on our IT folks to make sure that she could get access to the data and software that she needed to get it done. And through all of her persistence, I mean, we had issues with data as well, but she's been extremely persistent and has definitely worked hard to be able to give her presentation today. So I will let Casey take it from here.
Okay. Hi guys, last but hopefully not least. My name is Casey. As the title implies, I'll be talking you through a comparative model of exposure to indoor PM2.5 of the data coming from Nigeria. So we're just going to step you through the whole process. I'm going to try to provide some background and context. I'll explain what goals and objectives I had, how I compiled the data. As Dr. Mills hinted, there were some hoops, the results, and then what we think the implications are from those results. So we're just going to start. So I didn't know what kind of knowledge base people were coming here to, so this is just a real basic, what is PM2.5? I like this infographic. PM10, as you can see, is the blue dots, and that's what would be a single strand of hair. So PM10 already is very, very small. We're going even smaller, PM2.5. 4 to 5 particles can fit across one PM10 particle. So, and research has shown that because these particles are so small, they can get a little further down the lungs and cause a little bit more negative health outcomes. And it's been linked with respiratory disease, cardiovascular disease, and even higher mortality. And in fact, the International Agency for Research on Cancer named it a carcinogen in 2013. And so, of course, as with most things, the WHO, World Health Organization, does provide recommendations as far as thresholds for exposure. They do use the ambient thresholds for their indoor air pollution as well, and the daily threshold, which is in bold, because that's really what we're going to be focusing on, is 25 micrograms per meter cubed. The annual, you can see, is lower, and that's simply because if you're more consistently exposed for a longer period of time, you probably want that exposure to be a little less. Concentrations overall on both of those thresholds or those recommended guidelines are low because there's not a safe low threshold. There's no cutoff point that science is really strong-minded and said, nope, anything over this is dangerous. It's a very hard thing to identify when you're dealing with air pollution. So we're going to kind of take that for each step and apply it to in the home. So there's been a lot of studies looking at indoor air pollution in the home specifically, and especially in low and middle income countries. So they've consistently shown that PM2.5 is related to decreased lung function. We also have a lot of studies linking it to hypertension, cardiovascular disease, stroke, mortality. And for the first 2 points, I did provide an example just to try to put it in context numbers-wise, because we're going to be talking about numbers in a little bit here. So not only is 10 a nice round number and easy to apply to other things, but both of these studies were focused on women in rural China, so a low and middle income setting. And so I thought that as far as extrapolating to my data would be a little bit more close to what we were looking at. They also were focused on adults. There's a lot of data out there on child exposure, and I didn't want to factor that in too much. So there's also a lot of negative birth outcomes. That's been more and more recently. We're finding negative birth outcomes such as low birth weight and also preterm birth. But there's a lot more variation in those findings and where those cutoffs and how much exposure before use and where during pregnancy is the exposure most important. So I didn't want to put a big quantifiable number up on the screen for later on. This is important because in low middle income countries, biomass is used as a fuel source. It's used to cook, it's used to heat the home, and these homes are not well ventilated. And so we operate under the assumption that the exposures are much higher, and also that women are more greatly exposed because you're dealing with usually more traditional gender roles. Women are in the home more than the men. They're doing the cooking and the home care and things like that. Which leads me to what I wanted to look at. So this is very worried, but basically I had 3 goals. The first was I wanted to identify the different fuel sources in the home, and I wanted to see whether or not those different fuel sources did or did not reduce exposure. The second aspect was I really wanted to illustrate that the exposure in the home was high, and especially when you compare it to WHO guidelines that we just discussed. The last part, which is where we get into something that's not been done terribly often, and why this is kind of what I thought was very interesting, is developing a comparative model of exposure between primary and secondary members in the same household. A lot of studies look at women and across many households, but not within the same household. All right, so to try to put all of my results in context, I'm going to try to summarize in a clear way how I got my data put together. So I had the HAP study, which is the household air pollution study. It's a very large birth outcome study Dr. Norcross has been working on. And so obviously birth outcome, we're dealing with only women. And they were recruited at 18 weeks gestational age from public health clinics in Nigeria. They were interviewed to make sure that they were indeed the primary member of the household, primary cook, that role in house belonged to them. After all of these women were enrolled, they went back and made the BLD study, which is nested within the HAP study. So these members were recruited from the same household as the HAP women. But they're not just women. It can be women or men. And they were, again, interviewed to make sure they were the secondary member of household. So after all of this was done, the HAP data was a very large data set. The BLD not so much, because I believe they're still collecting. So when we merged, we ended up with about 33 household pairs. So this can be a little confusing, but the takeaways from this are that the HAP women, because it's a birth outcome study, some of them had multiple exposure measurements per household. Well, when you're merging data, we wanted one observation per household. So I did a little reorganizing to do that. But the takeaways are that 18 of the HAP women had both second and third trimester exposures. If they did indeed have that, I just averaged it together to get one exposure measurement for that primary member of household. But 15 had one or the other, for a total of 33. So what I ended up with were these exposure variables. Obviously the largest pair is going to be primary member versus secondary member. And if I slip and say HAP versus BLD, I hope you'll follow along because I am sorry about that. And like I said, the primary members had a little bit more complex exposure measurements taken. So second and or third trimester. If they had both, it was averaged. And then ultimately what I did was, depending on which was available for each household, I created a summary variable, which was an overall. Every household had an exposure measurement, and it paired cleanly with the BLD. So there were 33 exposures for HAP, 33 exposures for secondary BLD. I tried to keep my data analysis pretty simple. I used Excel. We did log transform the data to get some more normal distributions. I used paired and independent t-tests for difference of means. And then based on what the difference of means test showed us, we did a lot of regression modeling to try to really pinpoint what that relationship is or is not between members in the same household. Okay. So the first thing is just some basic info here. Like I said, 33 females were primary members. Their ages were ranging from 19 to 41, and the mean hung around right around 28. The secondary members had 15 males and 18 females, so pretty close to an even split despite the small sample size. Age range very similar to the primary members and with just a slightly higher average age. If we look at the distribution, you can see that the primary member exposure is much wider range than the secondary member exposure, as well as hovering a little higher. The other really important thing to look at right here is this black line right down along the bottom here. That is where the WHO guideline is, that 25 micrograms per meter cube. So already we can see that the majority of these exposures are much higher. So we'll start with just the basic difference of means test. I had all those exposure groups. So all I did was take the primary member exposure group compared to the secondary member exposure. We ended up with two significant p-values. Primary member the third trimester exposure was significantly higher than the secondary member exposure. But more importantly, overall primary member exposure was higher than secondary member exposure, which I hope to see and was excited to actually see. Because of that overall finding being significant, I wanted to see if gender played a role because we did have males and females in the secondary members. So I just stratified by it. So I took secondary member males and compared it to the primary member exposures. And again, significant at 0.03. However, what's also interesting about this table is that females, despite these females also being secondary members of the same household, it was no longer significant, indicating that even though they're secondary members of the household, their exposure is a little higher. Now this was probably the most surprising thing I came up with. We had three stove types, or fuel types. We had clean cook, which was an ethanol fuel, firewood, and then lastly kerosene. And I compared all three. This is not based on pairs, this was just exposure measurements. If we factor all of them in, there was no significant difference between fuel types. But because we had just learned that male exposures are significantly lower, we removed those exposures and did just the women. But still, while the values changed slightly, still nothing came back significant. So as I said, my last goal was to develop this comparative model illustrating the relationship between primary and secondary members. As you've probably already been able to tell, it wasn't there. It wasn't there. So we literally just paired primary and secondary members just as we did with the t-tests and plotted it, and obviously the linear regression, line of best fit. And if you look at the R-squared value, it's pretty low. it's about as close to zero as you can get. So unfortunately, I couldn't find a relationship. I really thought that if the primary member was more highly exposed, so would the secondary member, but that correlation didn't seem to exist. I also did the models for all of those exposure variables. None of them had a significant or even remotely strong relationship. And we also did some multiple regressions so that we could factor in age of all the exposure participants, gender, location, and also stove type. But again, nothing came back significant. So I'm not going to bore you with a bunch of graphs. So the first thing we want to do is try to look at these concentrations in comparison with the WHO guideline. I highlighted the mean across all exposure groups. If the guideline is 25 micrograms per meter cubed, even the lowest exposed members, which would be the secondary members, just about double what WHO recommends is what you should be exposed to. And then if we come across to the primary members, we hover at about 3 times that. And even if you apply this through the min and max, the range of what the exposures were, again, you can see there's quite a range, which is not uncommon in air pollution studies. They're almost always hovering and or exceeding. The other thing I would like to take a second and apply here is way back in the beginning we talked about that 10 microgram per meter cubed increase in exposure being correlated with decreased lung function in that China study. And I chose that study because the population, despite being China, most closely related to what we were doing here. And at 10 microgram per meter cubed increase, you can imagine how quickly the health effects would compile on these women in these studies, especially when compared to the secondary member. So some strengths and limitations. It was a pilot study. We're dealing with a very, as you saw, small sample size. However, the strength was really how this data was collected. We relied on personal exposure measurements. We didn't rely on recall or self-reporting. And the things that were self-reported were also verified by monitors during data collection as well. The specificity of the comparative model could be seen as a strength just because it hasn't really been done at length yet. There hasn't really been a lot coming out that way. However, how generalizable, what were my results? If you had a similar setting, similar household structure, similar family structure, maybe. So I had 3 main conclusions. Overall, there does seem to be a significant difference in exposure between primary and secondary members of the same household. Gender does seem to be a major influencing factor, which makes sense when you think about traditional gender roles in these countries. The second part is that all exposure groups have exposures which exceed WHO. All right, and this has a lot of potential negative health impacts associated with it. So as far as future research goes, I think it would be really interesting to have a more long-term study where we really follow these exposures and see and monitor for these decreased lung function, increased blood pressure within the same household to see if those health outcomes affect all members of household the same or at different rates. And the last thing was that, unfortunately, there was no significant difference between fuel types in these homes. Now, I do think that this was largely due to small sample size because, again, we only had 33 pairs, and we stratified by stove type. You had anything from 6 exposure measurements to, I think, 27 exposure measurements between fuel types. So I do think if it was a larger data set, we'd be able to better identify those patterns, and maybe even that linear relationship would develop as well. I want to say thank you to Dr. Norcross for including me in this study. I thought it was very, very interesting. I really enjoyed working on it. And then also to Julian Su, who's a PhD student. And she was monumental in helping me get all the data I needed because the HAP data is in a million different files, and I was locked out of Strongbox for months. So she was really, really good about making sure I got everything I needed. So thank you to her as well. Any questions? Yes, sir.
I've got 2 questions. The first one is just, can you tell us a little bit more about how these exposure measurements were taken?
Oh, of course,
I mean,
yes.
were they taken whilst those were being used? Were they taken randomly during the day?
No,
And
so,
Can you repeat the question first?
sure.
Sorry, oh yeah, why don't,
Thanks.
because I think, why don't you do,
The mic?
because it's picking up the microphone from there.
Dr. Gray asked me to expand a little bit more on how the exposure measurements were taken. Did you hear that?
Thanks.
Okay.
Yeah, I got it.
Okay, so these women that were recruited, they were then randomized to either stay in the control or an intervention method, which was the clean cook. And they were personal exposure monitors for 3 consecutive days. And as I said, some women had multiple exposures, so it would have been 3 consecutive days during the second trimester, 3 consecutive days during the third trimester. Thankfully, the secondary members was captured the same exact way. So they had 3 consecutive day measurements. So we ended up with the same exposure variables on either side. Does that answer your question?
Yeah, that's great. That actually helps. My second question is with the, with that WHO standard, there's sort of 2 things here. One is, it's also got a time element. So
Yeah.
it's 25 micrograms per kilogram, I mean, per meter cubed, averaged over a day,
Yeah.
or average, they've got averaging times.
Yes.
So I was gonna ask about that, but the fact that these were long-term personal monitoring suggests that maybe that's an appropriate comparison to that.
Right, exactly, yes.
And then the second thing is, though, is I don't know about this area, and either you may know or Dr. Northcross may know, is the external environment a significant source of PM 2.5, in which case it could swamp the effects of the different stoves. And that could be why you're not seeing it, because you're following people who are being either infiltration from the outside, or they go outside, so they have other exposures that that are bigger than bigger than the ones that are coming from their cooking source.
I do know that there's data in this HAP study that accounts for that, and I believe another student did look at something similar to that. I believe, if I'm quoting it correctly, she followed the exposure data indoor and outdoor, or like modeled where they travel and where their exposure is greatest. I did not look at that data, so I can't speak for how much the outdoor influenced that. Just been too much. So I'm sorry about that. Anything else?
Nice.